So I'd like to start by thanking the Cornell Atkinson Center for Sustainability for the support of this seminar series. And then today I'm really happy that Benjamin Houlton can join us. Benjamin's the current Dean of the College of Agriculture and Life Sciences at Cornell here, and a professor in the departments of Ecology and Evolutionary Biology and of Global Development. He joined us from UC Davis, beginning his term on October 1st in the middle of the pandemic. And his research investigates how people, ecosystems shape our world, combining tools from microbial genetics, chemistry, data science, remote sensing, and modeling in global research studies. His mission is to increase science and solutions for the benefit of humanity, nature, and the economy. He was founding co-chair of the California Collaborative for Climate Change Solutions, working with researchers from key institutions to accelerate the translation of research findings into practical climate solutions. And he led the UC Davis John Muir Institute of the Environment with the goal of devising innovative solutions to the environmental sustainability challenges of the 21st century. He also directs farmlands carbon sequestration projects to improve crop yields and create new financial markets for farmers and ranchers. So thank you very much for joining us today, and I'll let you take over.
Great, well, thank you. It's a pleasure to have this opportunity to share some thoughts of mine, as well as some research on this incredibly complex challenge of climate change. And I want to first thank Peter for this opportunity and introduction, the Cornell Atkinson Center for hosting this seminar series, and all the students out there from our environment sustainability major and climate change minor. You know, it's awesome to think about how the next generation of leaders is part of this Zoom session here today. And I think climate change is an incredibly complex challenge that involves a huge number of moving parts. We're all aware of that. But the solutions that we're starting to demonstrate, whether they involve new forms of clean energy, climate smart farming, thinking about how to meet the needs of climate justice for those who are underserved, are on the tip of what we're starting to accomplish. So I feel a tremendous sense at times of despair when I think about the challenge in front of us, but it's matched by a sense of optimism for what the future can look like. So I'm going to share my screen here now and run through a few slides. Give me a moment. Okay, great. So at this point, you should just be seeing one slide at a time. Is that correct, Peter?
That's correct. It looks good. Yeah, thanks.
Great, thank you. So what I'm going to be talking about today is this idea of removing billions and billions of tons of carbon dioxide molecules that have accumulated in our atmosphere, largely through the combustion of fossil fuels, as well as some contributions from land use change since the Industrial Revolution, which is needed to secure our climate future. The idea that I'm going to approach today involving carbon dioxide removal is one that is deeply embedded within our planet's history, a solution that Earth has provided to provide climate stabilization within a relatively narrow band for over 4 billion years and counting. And yet, this solution is one that has a tremendous amount of potential in modern climate change. So the idea is what we call enhanced weathering, and I will go through a number of concepts related to enhanced weathering, as well as where we are starting to deploy demonstration scale opportunities with farmers and ranchers. Now, I like this image of David and Goliath because we are faced with a moonshot issue when it comes to climate. And that rocks, much like the rock or stone that David was hauling over to Goliath is one possible solution that we should really be thinking about as we start to imagine a world of what we call negative carbon emissions. The challenge of climate, however, doesn't make much sense unless we talk about the manifold challenges that we're facing, which are superimposed upon a global climate challenge. By 2050, it's estimated that Earth's atmosphere will approach 550 part per million CO2, which, according to most measurements involving ice cores and other geochemical proxies, has not been seen in the atmosphere for perhaps 20 million years and counting. This CO2 in the atmosphere is imposing a tremendous amount of risk today and will impose risks that grow over time. These risks involve the destruction of infrastructure through natural disaster events, which are tied to climate forcing and elevated CO2, rising seas, which are impinging upon communities, issues related to droughts and wildfires and heat waves, which are exposing vulnerable populations to risks of comorbidity and mortality, as well as tremendous strains on our ability to continue to grow food. Here I talk about the 10 by 10 by 2050 challenge. Let me tell you what I mean by that. 10 billion tons of CO2 is the number that most of the models are converging on for the amount that we have to remove from the atmosphere starting by 2050. I'll take a look at some data on that in the follow-up slide so we can show you what that really looks like within the context of what we call the Paris Climate Agreement. We also know that we're going to be approaching approximately 10 billion people by the same time. This is an incredible challenge when we look at the fact that already on the planet, around 800 million people are estimated to be food insecure or suffering from hunger, and 2 billion people around the world suffer from micronutrient deficiencies. Current Earth's population is about 7.8 billion people, as most of you probably know. So we have to find ways to not only solve the climate challenge by radically cutting emissions and engaging in large-scale carbon capture, but we have to do it in a way that creates more nutritious food options for people around the world. This is the challenge of our time. Now, taking a look at what this means within the context of the Paris Climate Agreement, which is the way in which governments organize to figure out what their nationally determined commitments can be to help slow the pace of global climate change through radical approaches that cut greenhouse gas emissions going into the atmosphere and can help facilitate carbon dioxide removal so that the CO2 in the atmosphere can be put into a form that no longer induces global climate warming. This is a model, and there have been many other models since this one from 2016 that have come to relatively similar conclusions, although the ensemble of approaches that will ultimately be needed to solve the climate challenge are very much under debate at the moment. So in 2015, you can see here as identified this wedge in gray. Those are what are called the internationally determined commitments by countries that have signed on to the Paris Climate Agreement, which the United States recently re-entered with the Biden administration. This black line is what's called net carbon emissions. And this is the pathway to the future in order to hold Earth's temperature to no more than 2 degrees of climate warming compared to the pre-industrial time. In order to do that, we need to both radically cut emissions going into the air through energy, fossil fuel, industry, and land use change. And we have to start creating more carbon sinks on the planet so that we can hit a point of climate neutrality or carbon neutrality somewhere around year 2050. Now, as I mentioned previously, at the same time, we're trying to deploy these opportunities to solve the climate challenge. The world's human population is going to be growing to approximately 10 billion people. So the 10 by 2050 challenge is about radically capturing 10 billion tons of carbon dioxide from the atmosphere by 2050, while we find new ways to efficiently grow food and meet world hunger of 10 billion people. Now, one of the big opportunities that you've probably heard about, there's a lot of conversation now in the media as well as policymakers, is this idea of using the soil as a system to capture atmospheric CO2. Now, it is true indeed that our soils store somewhere around 2,000 to 5,000 billion tons of carbon, depending on the estimate you look at. But the truth is, we've lost a lot of carbon from our soil over time through land use conversion. So the idea is to start capturing that carbon back into the soil through various mechanisms involving soil amendments, involving new ways of boosting photosynthesis through crop breeding, as well as finding alterations to the soil microbiome that can allow that carbon to stick around for longer periods of time. I like to call this the Giga-ton economy, which is farming of the future, creating new markets and new opportunities for farmers to not only engage in practices that continue to support a healthy food system to meet the needs of a growing world population, but also start to catalyze the world toward negative carbon emissions. I was involved in this report that was produced by the Energy Futures Initiative. It's called From the Ground Up. And in that report, we go through a number of possibilities where exciting new research can meet the needs of this carbon challenge in front of us. Today, I'm going to focus on one particular aspect of carbon farming or carbon dioxide removal into the soil, which involves enhanced weathering. Enhanced weathering is pretty simple. It's grinding up rock or taking advantage of rock dust that has accumulated in mines over time of a certain chemical composition and adding that back to the soil in a way that allows that rock to act as a sponge for atmospheric CO2, taking carbon from the sky and putting it into the soil. The exciting thing about this approach is it really involves repurposing waste streams to help solve other environmental challenges while assisting our farmers and ranchers as they start to find ways to produce more food that's of higher nutrient quality. This rock dust has a lot of potential to solve multiple challenges at once. So I'll start by talking a little bit more about this idea of enhanced weathering, where the idea comes from, why we think this sort of low-tech solution has tremendous capacity for carbon dioxide removal on the planet. And then I'll start to focus in on a project that I have been leading with my colleagues in California, which we call the Working Lands Innovation Center. And in that project, we are working with farmers, ranchers, industry, government, and tribes in large-scale carbon dioxide removal projects involving silicate rock dust, biochar, and composted manure. I'll then present some preliminary results of the Working Land Innovation Center. Basically, we've been deploying these soil amendments for approximately 1 year, and we have some interesting findings that are coming out of the project. And then I'll take another step back and talk a little bit more about this notion of carbon capture with benefits. And I believe that's the best pathway to scaling out carbon dioxide removal. But not only do we get benefits which are broadly distributed when we remove CO2 from the atmosphere and lock it up for long periods of time. But we also produce many other benefits for our food system and for waste repurposing, allowing for economies to start to develop real live market solutions that are dedicated to carbon dioxide removal. So in the next slide, I'm going to focus on this idea of enhanced weathering, the history of our planet in just a couple of slides, and how that provides the foundational science to start exploring enhanced weathering as a carbon dioxide removal strategy that can be deployed to deal with climate change this century. So let's start from the beginning, something that we're all aware of, although oftentimes we don't think about. We live in the incredible Goldilocks spot. If you remember the story of Goldilocks, it's not too hot, not too cold, the porridge is just right. The bed is not too hard, it's not too soft, it's just right for Goldilocks as she enters the bear's domain. Well, we know that Earth is in that just right habitable zone where we can have liquid water, a relatively stable climate, and an active biosphere that evolves over time, whereas we can compare it to places that are too hot, like Venus, or too cold, like Mars. So we like to think about this Goldilocks as largely being driven by the fact that the Earth is situated at the right distance away from the sun, so we get just the right amount of incoming solar radiation to keep the planet relatively warm and to keep liquid water as a principal component of the hydrologic cycle. But there's actually more to this story than simply this idea that the Earth is positioned correctly in its orientation compared to the sun. And in fact, much of the story of Goldilocks comes down to the climate stabilization, this amazing built-in feature of planet Earth that allows the climate to respond to changes in carbon dioxide that can occur naturally, or Earth's temperature as the wobble and the eccentricity and the precision of the Earth. That would be the orientation around the sun, which takes place over 21, 44, and 100,000 year timescales, which alters the Earth climate. Well, we have these built-in feedbacks between the rocks, the living component of our planet, and liquid water that results in what's called a negative feedback or a climate stabilization, so we don't end up looking like Venus or Mars over time. And the way this works in the simplest way possible is that we have calcium and magnesium silicates. When those rocks break down, they consume 2 molecules of CO2, which are converted in that process to bicarbonate, which is an ion that dissolves in water and can ultimately wash away to the ocean, where it can reprecipitate back out in a relatively high pH ocean environment as calcium carbonate, releasing 1 CO2 back to the atmosphere, but storing the carbonate over long time scales. And this is why Earth's atmospheric CO2 composition has changed by many orders of magnitude since Earth first formed, because these rock weathering reactions consume carbon dioxide and convert it into a permanent, semi-permanent form of calcium carbonate or limestone, dolomite. You might be familiar with some of these various rocks. Well, that in and of itself helps to provide the opportunity for carbon dioxide to not accumulate to levels that allow Earth's climate to get too hot with a runaway feedback like Venus. But the real secret here is that these reactions happen faster when we have fresh rock being exposed to Earth's surface and temperature increases. But they are slower when we have less fresh rock at Earth's surface and temperatures go down. So in other words, as temperatures go up, the process through which the rocks break down and consume carbon dioxide increases, resulting in stabilization on the rise of CO2 in the atmosphere. But when Earth's climate naturally cools, these reactions slow down so that the carbon dioxide from volcanoes starts to accumulate back in the atmosphere, resulting in some warming. And one thing is very clear about greenhouse gases: if the Earth didn't have its current composition of greenhouse gases, we would be approximately as cold as Mars. In other words, water would be frozen. So greenhouse gases are incredibly important for maintaining Earth's climate system, but it's really that sweet spot, that Goldilocks, where there's not too much and not too little, that helps support the planetary system over time. So I like to call this 2 CO2s enter, but only 1 CO2 leaves. Now, terrestrial silicate rock weathering is much more complicated than a couple of equations that I just showed you. In fact, there's a huge amount going on when it comes to silicate rock weathering. An incredible amount of science has taken place over many, many years to explore the controls over the weathering process. Silicate rocks in particular, those derived from volcanic materials such as igneous materials, are those which are most capable of storing carbon dioxide over long time scales. And so we've really focused on rocks of volcanic origin when we think about carbon dioxide removal. Well, currently we estimate that about 0.5 billion tons of carbon dioxide are removed naturally through relatively slow weathering reactions on the planet each year. There's a little uncertainty around these numbers, but it's approximately 0.5. Now, if you go back previously, I talked about emissions being around 40 to 44 billion tons per year. So you can see that this in no way can stop the current pace of global climate change with respect to the amount of carbon dioxide that fossil fuel combustion, human activities are currently putting into the atmosphere. But it is interesting to note that there is this carbon sink that naturally occurs through the weathering reactions on the planet. Now, as mentioned, some of the controls on these reactions involve temperature. The warmer the climate, the warmer the environment, the faster these reactions go. Acidity, and that would be the more acidic the soil or the more acidic the environment when it comes in contact with these kinds of rocks, the more quickly these rocks will dissolve and break down. Water availability and flow path are extremely important. Water is the solvent that combines with atmospheric CO2 to produce carbonic acid, which I showed you previously, that can then facilitate the breakdown of these rocks and accelerate weathering reactions. Denudation rate, and this is just a fancy way for saying uplift rates, more or less, or it's a combination of what we call physical erosion and chemical weathering of rocks. Both of those are operating at all times. So the faster the uplift rate, the faster the rock is being exposed to the atmosphere, the more intense and the greater the kinetics of the weathering reaction, all things held relatively equal. And then finally, a critical component is mineralogy. What is the rock composed of? Does it have olivine in it? Does it have pyroxene? Is it mainly quartz? Different minerals are weather at different rates. And so the mineralogy is incredibly important in terms of understanding the capacity for different rocks to result in carbon dioxide removal, either naturally or through enhanced weathering. I want to point out that two of the major constraints on the rates at which rocks naturally break down are mineralogy, which I mentioned, and denudation. And that's because we're talking about mountains, which are relatively large slabs of rock. What happens if you break the rock down and you, in essence, start to produce very high surface to volume ratios for acidity and temperature and water to begin attacking the rocks. Well, that's the idea behind enhanced weathering. Crush the rocks to accelerate the weathering process so that we can take what we know is nature's solution or nature's natural climate breaks that operates over millions of years and make that happen so quickly that it starts to put a dent into global carbon dioxide concentrations in the atmosphere. Crushed rocks can be deployed through standard equipment. Here I'm showing a calcium silicate that can be dumped into a farm field. Carbon dioxide can be supplied from root and microbial respiration and atmospheric exchange. So rather than waiting for these reactions to happen slowly over time deep in the geology underneath the soils, we bring it up into the soil environment where there's a tremendous amount of biological and geochemical activity that is cranking up CO2 concentrations and allowing for these reactions to happen even quicker. Soil pore water can come from irrigation and precipitation. Both of those can help facilitate the rate at which the rock breaks down. And then we go back to our fundamental equation where we have CO2s being converted into bicarbonate. Initially, we can store 2 moles of carbon through every unit of weathering reaction. But there is the possibility that some of that weathered bicarbonate will be converted into calcium carbonate nodules in the soil. It looks like little limestone, which would mean we release 1 CO2 back. So in this case, we only sequester 1 mole of carbon versus 2. Either way, it's an incredible opportunity to start thinking about how we can accelerate the process through which we remove carbon dioxide from the atmosphere. So I just mentioned carbon can be stored in the soil as carbonates or as ions that are precipitating back out. And it can also make its way out to the ocean, which is one proposed benefit of this approach, given that the oceans are becoming more acidic as carbon dioxide rises, the concentrations increase not only in the atmosphere, but in the ocean. This can provide a buffering to that acidity, which can help mitigate against not only climate change, but ocean acidification as one possibility. We have a huge amount of uncertainty on these ideas. It was probably in the early 2000s or mid 2000s that this notion of enhanced weathering started to make its way into the scientific literature. And there's been a number of experiments which have tested the efficacy of carbon dioxide removal using various mineralogies of rocks, various amounts of rocks in different environments. But most of these studies, the vast majority, have taken place under laboratory conditions. And if you were to scale up some of these estimates, you might get numbers as high as 200 billion tons of carbon dioxide removal for enhanced weathering. That is the absolute way upper bound. That number should not be taken seriously. That's more just like global scale capacity if we were to deploy crushed rock throughout soils on the planet. And some of these lab results are based on really the best conditions possible for weathering reactions, so you get these extremely high numbers. We know that nature is much more fickle than that, with a lot of variation in space and time across different systems. The average that we estimate, this is based on work from my student Iris Holzer, is somewhere close to around 20 billion tons of carbon dioxide removal when you scale up lab studies. Field studies, now there haven't been many, there's only been 3 that we were able to identify that looked at moderate scales of rock dust additions into the field, have found much lower numbers, closer to around 2 billion tons of CO2 removal if these rocks were spread across agricultural soils on the planet. Models have also suggested much lower numbers, but if you add all these together, you come with a mean of about 2.8 billion tons of CO2 removal, again, if the rocks were applied. In this case, we're assuming it's basalt. So kind of your garden variety volcanic rock that's crushed up in a fine way and then applied to the croplands around the world. Still, 2 billion tons or 2.8 billion tons is a very big number when it comes to the possibilities for carbon dioxide removal. And these are just estimates that are based on per hectare of land. One of the more exciting ideas behind enhanced weathering is the co-benefits that can be generated. And this was put very nicely by a paper published by Berling et al. In 2018 when they started about farming for the future with rock dust. One of the nice things about rocks is they're not only great at acting as a sponge for carbon dioxide removal and securing that carbon dioxide for long periods of time, but they also release nutrients which are vital to plants and soils and microbes in our cropping systems. Some of these nutrients involve phosphorus or magnesium, potassium or calcium. And in past studies, there's been evidence that largely from greenhouse studies, you can see increased crop yields with rock dust addition. So they can provide both macro and micronutrients, the macronutrients being phosphorus, nitrogen use efficiency enhancements, magnesium, potassium, but also it's estimated that micronutrients can be derived from rocks, especially zinc and iron, which are becoming diluted in our global cropping systems as carbon dioxide concentrations rise. And I will return to that topic at the end of my talk. They can help rebuild eroding soils. Currently on the planet, it's estimated that there's over 30 billion tons of soil erosion each year. So we have to find ways to first halt erosion using better management practices, and in addition, grow soil to secure our food system for the future. And the silica, which is released, also is quite important for many of our crops. It helps with resilience. A lot of our crops can use that silica to produce stronger stems so that when wind disturbance events come by, you don't lose the entire crop. And it can also help with fungal load because silica is incredibly important to reducing the amount of herbivory that can take place in our cropping systems. Finally, there are other greenhouse gas benefits that can emerge. As rock dust is applied to soil, there's a number of studies that have demonstrated that the fertilizer is used more efficiently by the crop, meaning that less is lost to the environment, which can help farmers with their bottom lines, but also that results in reductions in N2O emissions. Now, N2O, for those of you who aren't aware, is the third most important greenhouse gas on the planet. It's currently associated with around 6% to 7% of global climate change. And much of that comes from fertilizer use in our soil. So reducing N2O emissions is another possible benefit of rock dust as it alters the pH of the soil and reduces microbial processes that emit nitrous oxide gas. So the bottom line is enhanced weathering is a pathway that we imagine can help to securely lock carbon into a form that is stable over thousands of years, and it has an array of useful co-benefits that are vital to our farmers and ranchers and society more broadly as we think about the nutritional quality and density of our food supply system. But a lot of these ideas are still very much in the hypothesis stage. These are thoughts that have emerged through the scientific community, but much has not been tested to verify whether these benefits do reveal themselves, where they don't reveal themselves, and what the right mix of rock dust is for farmers to start maximizing yield and reducing fertilizer input costs while providing carbon benefits. So about 4 years ago, we started thinking about this in my lab group when I was at UC Davis before I moved to Cornell. And This is a project that was started, and I want to give all credit to Aaron Menego, who started thinking more about rock dust and whether there were benefits of different minerals as well as different kinds of rocks that can be applied to the soil. And she took advantage of an existing research site at UC Davis, which is called the Russell Ranch Experimental Agricultural Sustainability System. And she started exploring different kinds of ground up minerals and rocks and how that might change the yield of corn at about a quarter-acre plots. These are results from the first year of her study, where she examined control, where no rock was added, gypsum, which is a calcium sulfate. It dissolves very quickly and it's widely used by growers in California and elsewhere for water benefits, water use efficiency. Wollastonite, which is a purified form of calcium silicate, and then basalt, which is a mixture or ensemble of various minerals and has a pretty good capacity for nutrient benefits and carbon dioxide removal. She explored this across conventional systems where we're applying pesticides and fertilizer consistent with how growers are typically producing corn, and compared it to an organic only set of treatments. And what she found is really interesting, that overall, the benefits are about an 18 to 26% increase in corn yield across both conventional and organic treatments. And the treatment effect here was statistically significant across her preliminary studies. So this supports the idea that there can be realized yield benefits, which are highly localized to farmers when they start engaging in practices involving various forms of rock dust addition. I'm going to hit pause here quick and look at the Q&A because I see a couple of ideas or thoughts coming up. Okay, I'm going to try to answer some questions as I go along, and then I'll save some questions for the end. I just want to make sure we fit everything in on time. So number one, can enhanced weathering aid in the growth of a wide variety of crops, or is the scope limited to a certain number of crops? Great question. I'm going to show you some results in this talk from alfalfa and talk to you about the various cropping systems that we are exploring enhanced weathering in. But there is a lot to understand about what kinds of crops, what kind of growing conditions are best for understanding the efficacy of rock dust. How much energy to crush and transport? Another great question. It can negate some of the positive benefits. So this is an area we are currently exploring through life cycle assessment modeling. Much of the rock dust that is being examined for enhanced weathering is a byproduct of the industry, meaning there's not new mining operations that are needed. It's just taking some of their waste product and repurposing it. And that can get us to a pretty big number of carbon dioxide removal potential on the planet. But we are very much aware of transportation, which can chew into the carbon benefits. Current estimates say that maybe 20% of the carbon benefits are lost through transportation. And that's something that we're currently starting to figure out by optimizing both the economics as well as the full greenhouse gas benefits over the life cycle of the rock itself. So there's another one very similar to that. What is the cost? I'll show you that in a little bit. Thank you for asking that question. And then there's a question about saturation. Great question. We just don't have a good answer to that yet. It's unlikely that we would see carbon saturation happen over decadal scales in most of these systems, but certainly eventually you may get some carbon saturation. But carbon saturation is a very uncertain part of global soils or soil carbon farming in general. And while it was widely thought that we would see a lot of saturation with different practices, it's not always showing up in long-term studies. Okay, so now I'm gonna go back to the talk, and then I'll go back to questions. And maybe some of the questions will be answered in the next several slides, but thank you, really terrific questions. So based on Erin's really great initial studies, and she has explored a lot more, which I'm not going to get into, involving carbon sequestration and the nutrient quality of the crops themselves. She has some really exciting work going there. We realized that one of the great deficits was sort of demonstration scale, working with real farmers and ranchers in their systems so that we could really understand what are the barriers, what are the benefits, and how can we start to showcase where rock dust is an incredibly important opportunity for carbon removal and yields and nutrients, and also what are the limits to some of these approaches. From a scientific perspective, it's incredibly important that we get the science out in front of some of these questions, but we have to do it in a way that we're working across scales with stakeholders. And that's one of the ideas behind the Working Land Innovation Center, where we've been testing soil amendments for climate mitigation across both California rangelands and agricultural lands. And this work was supported by a number of grants. The biggest was from the California Cap and Trade Market, which is their carbon pricing mechanism, which led to a competitive call for proposals on carbon dioxide removal, funded at $5 billion initially from the Strategic Growth Council. It ties in a huge number of partners, including Ag and Natural Resources and Cooperative Extension in California, UC Davis, where it was centered and still continues to be centered. I still maintain a PI position there to oversee the grant. UC Berkeley, Wendy Silver at UC Berkeley is the co-PI. California East Bay, where we're working with Patty Awakawa and her group on rangeland carbon sequestration using flux towers. USDA, especially the Climate Hub in California, the Berkeley National Lab, where we are evaluating large-scale models and the development of model-based tools for decision makers, and the University of California, Merced, where we are working with researchers in extension. Of course, now I need to add in this exciting other component that Cornell CALS is involved, and we are starting to explore the idea of creating a bi-state operation that's exploring enhanced weathering and other carbon amendment approaches, both in New York and California. So we are a consortium of researchers working with private farms, UC extension centers, industry partners involved, including those in the mining industry and the agricultural industry, government, and tribal groups. We have been exploring how we can start to take advantage of what's called traditional ecological knowledge from tribes in California and engage in carbon farming demonstrations with them in the project too. So it's a really incredible group, and we are learning so much by having the stakeholders not come in at the tail end, but they've been in the trenches with us, trying to understand how to do the research since the very first day. And I think that's an important lesson for how we need to start sorting through, in a really quick way, the barriers to adoption in carbon dioxide removal. So again, just to refresh your memory, we're talking about using a slow, natural geologic process, making that happen quickly by pulverizing the rock, taking the rock dust and adding it to the soil. And these are pictures from our actual plots where we've been deploying some of the rock dust in our row crop systems, and adding organic matter too, because we believe some of the most exciting synergies will involve not just the rock dust alone, but the rock dust in combination with biochar and compost. And the compost we're working with is derived from dairy manure. So we're finding new ways to repurpose some of those waste streams in terms of fertilizer and carbon benefits, which can combine, we believe, in what's called mineral associated organic matter, or very long-term organic carbon storage that can happen in the soil. In terms of the geography of the project, we have spent about the past year and a half deploying over 100 acres of carbon farming demonstrations. I'm showing a lot of the sites here. There was a question previously about which crops we're working in. Well, right now we are focused on corn because of its global significance. Alfalfa, again, another incredibly important global crop for animal systems and animal production. Tomato, which is much more localized to Yolo County in the northern parts of California, so incredibly important for the local economy. And then we're also exploring opportunities in orchard crops. And in this case, we're working in almonds, which are widely abundant in California, the second largest crop by area in the state. In addition, we're focusing on managed grazing lands. We're applying compost and rock dust in combinations into rangeland environments where there's active grazing happening, working with private ranchers up and down the state in different bioclimatic regions. And then we have studies where we have both rangelands and cropping systems working side by side. I'm not showing all the locations because some of the locations are kept private, especially with our private ranchers that we're working with. But these are the locations which are freely available to the public. And you can see that we're spanning areas north. Here's, for those of you who are a little bit unfamiliar with California's full geography, this is the Bay Area, so San Francisco. Then we go down here to LA, and then we go down to San Diego, and this is called the Imperial Valley, which is an incredibly hot region in California where there's a tremendous amount of alfalfa production. So we're spanning quite a bit range of different environments throughout what's known as the Central Valley region of California. And then we're also looking at some coastal areas, especially with rangeland carbon farming, and then again down into the Imperial Valley. So before I turn into some of the exciting results, let me go back to our question list, try to keep a little handle on the list. Okay, can you share the energy cost of crushing and how much? Okay, so I think we kind of touched on that a little bit, and I will go in more detail into the challenge of energy production, but the rock dust that we're working with is a byproduct of the crushing process. The mine that we're partnering with in California is 80% renewable powered. And we're also trying to keep the supply chains very close to proximity to that mine so that we are radically reducing the carbon footprint. But my guess is in order for this to become a widely adopted global carbon dioxide removal strategy, we need to figure out how to work with local mines instead of shipping materials all around, which would cut into the carbon benefits. Next is the idea that field applications would be one shot or repeated. Yeah, I think that the idea is that this will be repeated. The frequency at which it's repeated is up for debate. We've done some global scale calculations that, again, I think are still highly uncertain, but suggest that 5-year additions of rock dust to 11% of Earth's land surface, that would be the global croplands on the planet, could result in around 2 to 3 billion tons of CO2 removal each year. So that's over a 5-year domain. All you need to do is figure out what happens if you do it over 1 year. You might get to 10 billion tons. But again, those calculations are really guesstimates at this point. I wouldn't, take those and say these are the actual numbers, not yet. How quickly do the crush rocks take to grab the carbon dioxide? That's another great question. We are exploring that question in field settings across different climates and in growth chambers to say what happens when temperature is high, what happens when you change the growing conditions, what happens when you change the soil. And we're doing a lot of detailed experiments in the lab as well to understand the kinetics of rock breakdown. Next, can you explain that expected 2.8 billion tons sink enhanced weathering again? How many hectares of enhanced weathering and eating? So that number is assuming that 11% of Earth's land surface, that would be the global croplands on the planet, are deploying rock dust at around 20 tons per acre each year, every 5 years, according to that calculation, as I said before. So that's a big part of the capacity, says we do this on the planet, and we assume sort of an average chemical weathering rate, and then we estimate the amount of carbon dioxide removal that would happen. Again, these are just capacity terms. Don't take those numbers, write them in stone, no pun intended. We got a long ways to go before I have any confidence in those numbers, but it is interesting that you just do some simple calculations based on the chemical properties of the rock and what we understand about rock weathering reactions, and you can get big numbers relatively quickly. Okay, I'm gonna take a break from some of these exciting questions and get back to going through the talk here, if that's okay. I love the excitement though, it's awesome. Okay, let's see. Frozen computer, there we go. All right. So one of the really real benefits of a lot of soil amendment practices is we don't need a bunch of new equipment that most of our farmers don't already have access to, either through cooperatives or their own pieces of equipment. This is just your basic spreader that most farms that are relatively decent scaled have in order to spread manure and other things onto their fields. And this is a large-scale demonstration in partnership with one of our wonderful farms in California, Bowles Farm. It's, I think, 7 generations in. They produce an incredible number and variety of crops, including alfalfa and corn, huge variety of vegetables, and cotton. Some of the world's best cotton can be traced back to Bowles Farm. So they've been working a lot on sustainability, and they allowed our research team to come in and partner with them. And I'll just show you this video so you can see how exciting it is when you add rock dust to the soil. Pretty simple, spreads the rock dust out. This is a metabasalt rock that was derived from one of our mining partners, Specialty Granules. And so they brought it over. It's not too far from the mine. It's about an hour and a half or 2-hour drive from the mine. And here they are just using their standard spreading equipment. In this case, we try to set up a standard scientific design where we have strips of rock that are being applied, and then we have control conditions in between the rock amendments so that we can understand the benefits relative to non-rock plots right next to each other side by side. And here's an aerial photo. This is based on some drone footage from Bowles Farm. After the application, this is one day after, you can see where the rock was spread across these different strips. This was a randomized design in terms of how close the strips would be to each other versus the space in between where we added no rocks. And it's incredible how nice it looks from the sky when they applied the rock. This is about 15 acres total, just to give you a sense for the footprint. So we're working now to understand the carbon capture benefits, the yield benefits using their equipment, as well as hand harvesting approaches so that we can examine the differences in approaches to quantifying yield. We are exploring water and nutrient use efficiency of fertilizer in these systems. Crop resilience is a question related to the silica that's released and the benefits. A question came up previously about how cost effective is this strategy. Right now, our estimate is that anywhere between $60 to $300 per ton of carbon dioxide removed. So what does that mean? Well, if we think of direct air capture as one approach that's widely discussed, that approach is typically around $500 to $700 per ton of CO2 removed. So in this case, we're looking at relatively cost-effective strategy by comparison to direct air capture, and the economies of scale may get better over time. However, there is a huge amount of uncertainty, and cost barriers are still prohibitive, especially when we get anywhere above $100 to $150 per ton of CO2 removed. Finally, as I mentioned, we're also looking at other greenhouse gases, in this case, nitrous oxide reduction that can happen. And I have a student her entire thesis is focused on that, Emily Guhagen, and she will be coming out to be a Cornell student very soon. She spent her first year at UC Davis and is using automated chambers and a field deployed Picaro analyzer to get real-time estimates of nitrous oxide, CO2, and methane coming from the different treatments. So now I want to talk over some of our preliminary results, what we're starting to find over a year into the project. And I'm going to focus on first, results of carbon dioxide removal, the amount of bicarbonate alkalinity that we are seeing in our soil water collectors. And this is being led by Iris Holzer, who is a PhD candidate in my group at UC Davis. She's been spending a lot of time in the field lately, following rain events, collecting water in a device called the lysimeter. You can put this under vacuum following a rain event, and you can suck in some of the water. And she's doing this in plots that are treated with a metabasalt and a metabasalt plus olivine. Olivine has incredible potential for carbon dioxide removal, but it does have the downside of potential heavy metal contamination of the soil because it's an ultramafic mineral that is found in basalt. So when you add purified olivine, you might get carbon benefits, but you might get some negative effects. And that's why we're testing olivine in the field. In this case, this is at UC Davis, so we're not doing it in the food supply system with our farmers. We're doing it at about acre scales to understand what the benefits might be and what the risk and side effect might be of using olivine. So the bottom line here is she's finding some incredibly exciting results, about a doubling of bicarbonate flux with rock amendments compared to control. And she's seeing this both with metabasalt, but the metabasalt plus olivine shows incredible potential for carbon dioxide removal. The olivine she added here was at around 10 tons per acre. So it's about half of the amount that we would add for metabasalt. We're not suggesting that 10 tons should be added to agricultural soil, but we wanted to apply a fairly significant amount so we could explore carbon and negative consequences possibly from the olivine. So really compelling results. More will be revealed on this, but this is, to our knowledge, the first time that there's been in situ estimates, that's on-site estimates at large scales across many acres of carbon dioxide removal through the process of enhanced weathering, and she's producing some super compelling results so far. In addition, we are finding evidence for an increase in yield in alfalfa. This is explored across 17 total acres of rock and controlled treatments. And so this is just showing the weight of the yield from several cuts that take place throughout the growing season under control versus rock treatment. We're still collecting a lot more data here, so I'm not ready to say that we are concluding that we will see strong yield benefits. I think in some cases, yield will go up, and in other cases, yields will probably not show much of an effect. And that's why we're exploring this across different crops and different systems, because we really want to get a handle on what yield can look like. But this is quite compelling when you consider an 18% increase in yield. That really does make a meaningful difference in what farmers are able to bring in terms of profits. Okay, in the last few slides here, I'm going to kind of shift to the issues as we understand them, talk about some of the opportunities for generating co-benefits, and then I'll open up to questions again. So first, this has come up in the questions. We have the same question. What is the kinetic of these reactions? What are the weathering products? What nutrients are released? What are some of the downsides of possible heavy metals that could come from materials like olivine? And what's the fate of the carbon dioxide captured? So it's going to take years for us to fully be able to address all these questions, but there is a huge amount of research and development that needs to take place to explore that incredibly important scientific question in front of us. Second, upstream greenhouse gas and environmental impacts. This is something we're giving a lot of thought to. If this is a widely deployed carbon dioxide removal strategy, but it's resulting in environmental degradation and new mines, this is defeating the purpose of what we're trying to accomplish. And so we are looking at how to optimize economics, greenhouse gas benefits, and environment, doing life cycle assessment analysis of the different materials. We'll also talk a little bit about sourcing of rock finds and slag. As I mentioned, the rock dust is being generated every day. It's a byproduct of the building and manufacturing industry. It doesn't currently have a market. And so this is taking a waste product and turning it into a usable good. But eventually, if this is deployed over a decade or so, we're going to have to start tapping in to new materials to continue to create carbon dioxide removal. And that's where slag and kiln can come in from cement, buildings, and steel manufacturing, which I'll talk to you about in a second. And then what are the barriers to adoption? I just want to pause here for a second that anytime we are deploying these kinds of studies, I am a firm believer that we need to have an inclusive approach that involves from the beginning all of our stakeholders. And this is one of the key ingredients of success that we're learning about in the Working Lands Innovation Center, including our farmers and ranchers in the studies so we can understand where challenges are for them, what they see as the issues in front of us. And we're doing a lot of surveys to examine what sort of carbon benefits they need to get in terms of financial rewards to feel like these strategies can be adopted. If we want our agricultural community to help us with the global carbon challenge and help us solve climate change, we need to pay them for those services. And I know that the Biden administration is very much interested in trying to figure out how we can do that using carbon credits. We also need to continue to cut emissions because carbon dioxide removal will not stop global climate change by itself. It needs to happen with radical emissions reductions from energy and industry. Okay, few more slides here. First, carbon capture with benefits, waste recycling. So this is produced by Berling et al. This is kind of a back of the envelope estimate of the next latter half of the century or moving forward to 2100, different countries and the amount of slag, kiln, and demolition materials for infrastructure that will be produced, slag and kiln coming from cement. We also have slag and kiln, which can come from steel manufacturing and then other forms of slag. But the bottom line here is there is a huge amount of silicate production in waste that can be deployed back into enhanced weathering that could help support carbon dioxide removal while repurposing waste streams. A huge amount of research needs to happen here to make sure that these materials are safe for our food system. But I'm pretty excited about the idea of exploring not only rock dust fines as a byproduct of the mining industry, but how we can repurpose other waste streams. Again, another possible carbon capture with benefit approach. Second, I mentioned this a few times, the world is starting to see evidence more and more for micronutrient deficiencies. We already see 2 billion people on the planet that don't have access to the right quantity of micronutrients. And a lot of that comes down to animal source foods and dairy operations, but plants need to provide those nutrients to support animals and support humans. In this case, this is looking at rice, and this is evidence for what happens to iron and zinc concentrations when you double carbon dioxide levels across a wide variety. If you're in the red here, it means that the concentrations of those nutrients are going down with elevated CO2. Green means they're going up. So both zinc and iron are vital to human functioning in enzymes, in brain function, so on and so forth. And you can see that we're starting to find evidence that we could be facing dilution of these micronutrients more and more in our future. Rock dust has a lot of iron and it has zinc. So it is possible that the rock dust could help to fortify our soils, which could offset some of these reductions, but we need a lot more study on that to understand the possible benefits. Finally, as I mentioned at the outset, 30 billion tons of soil are eroded from our land each year. This isn't just from our cropping system. This is from poor land use practices in general, but that's a huge amount of soil that is washing away, that is now causing risk to food security in the future. I like to point out that soil is not just organic matter. In fact, the organic matter we all get excited about because it provides water storage, it helps with nutrient cycling, and so it's such an important part of the soil. But 45% of the soil is minerals. Those minerals are derived from rock weathering reactions over time. I believe we need to start taking on the challenge of soil conservation, not only by deploying better practices like cover cropping and erosion control, but also thinking about how amendments can help restore, rejuvenate, and provide soil that's needed for a healthy future for people and the planet. So another possible benefit is growing soil for food security through pulverized rock, organic matter additions that can then amend the soil and return them to a state that allows for regenerative agriculture to start becoming more widely adopted by growers around the world. Okay, that's it for today. I know I have a lot of questions. I'm going to go hit those questions again. But first, I want to thank everyone who's involved. Maya Almaraz is the program lead. She's like the lead scientist who's helping to coordinate everything. So I'm the lead principal investigator, but she is really the glue that gets this incredible network together for Working Land Innovation Center. Nina Bingham is a postdoc extraordinaire. She cut her teeth trying to in understanding geology and weathering processes in natural environments, and now is using that scientific foundation to help us understand enhanced weathering. And I mentioned some of the others involved, like Iris, and then here's other members of the team, including Emily, who I mentioned, Aaron, and this is Autumn. So these are the members of the team. I want to thank the funders. So this has started many years ago through grants. They allowed us to start exploring rock weathering on the planet from the National Science Foundation, our partners like SGI and Rock Dust Local, the Andrew Mellon Foundation, Roger Sant and Doris Matsui, Boomerang, and the Strategic Growth Council of California. Okay, thank you so much. This is so much fun. I'm going to go to the questions here and get through as many as I can. I see that there's something like 48, 49. And some of them are really long, so I'm going to try to do my best and just hit a smattering of questions. So we did talk about the environmental consequences a little bit, and so we have to continue to explore those challenges. We cannot mine rocks and mine our way out of this problem without producing a lot of challenges for environmental systems, for biodiversity. That's why I'm a firm believer of using the byproduct of existing mining operations in terms of rock dust and starting to explore repurposing kiln and slag and other materials for carbon benefits. How long does the calcium carbonate last in the soil? Terrific question. Estimates are 77,000 years when you do simple turnover time analysis. If you look at the duration of that material, it will come down to future land use and acidity. If the soils become very acidic for whatever reason, or land use changes, it could mobilize some of that carbon, but it has a tendency to stick around for thousands of years. If it makes its way to the ocean in the form of bicarbonate, it can have a lifespan of 20 million plus years. Okay, so it is, in terms of the permanence side of the carbon challenge, it is an approach that has a lot of potential for storing carbon on a relatively permanent basis, especially when we think about the next 100 years, but nothing is really permanent overall. Next, a lot of strategies for sequestering carbon. The question that I have is, what will give us the best chance in the next 30 years, and what's scalable worldwide? We also need strategies that could be put in practice immediately. For instance, would it be better to move toward a plant-based diet that the world is seeing as opposed to animal agriculture? If we have 30 years to achieve this, one or more practice ways of removing carbon from the atmosphere? If so, what your work on rock dust could be used on plant-based? You know, look, I think there are a lot of questions right now. We have a lot of people suffering from micronutrient deficiencies. There is evidence that maybe in certain areas, people are eating too much food, too much protein. We know that obesity is a huge challenge. Our food system is not supporting a healthy population in some respects. We also have to understand that, you know, I like to point out dairy is an incredibly low carbon food when it's just in the milk variety. In fact, in terms of unit of protein, it's really among the smallest carbon footprints out there. But there are other forms of animal source foods that A lot of them come from areas in the Amazon where they're burning the rainforest. We need to be cautious about that. That is an incredibly complex issue. And if we're losing biodiversity in a way that is really not environmentally friendly to grow food, that is a challenge. But ultimately, these are questions for other days and for other people than me. We need to think holistically about human health. We need to think holistically about our food system. This strategy of soil carbon farming has the potential to scale quickly. The infrastructure is already intact. It doesn't require a bunch of new things out there, gadgets, widgets. The capital costs are extremely low. And so that's why we're going to continue to explore it. At the same time, I am not willing to say that this is going to be a huge part of the solution set yet. We still need a lot more science and a lot more R&D and demonstration scale verification before I'm willing to commit that, yes, this is a really great strategy and we should start working with it as a carbon dioxide removal. So we have to work quickly, but we got to let the science speak. Otherwise, we're going to end up in challenges again. How do we educate and encourage farmers? Oh, that's wonderful. Yeah, so in working with the USDA, we've produced a number of fact sheets on carbon farming. We talk with our farmers. We're having showcase demonstrations. Obviously, COVID has made that incredibly challenging because of the need to be safe and have social distancing, but we had planned a lot of showcase events. We're still planning on doing a lot of online events, and we're working with cooperative extension. So I think there's a lot of possibilities there, but certainly we have a long ways to go. This is why I'm a firm believer. You have to bring farmers and ranchers into the studies early and then allow them to be a part of the science that you're exploring if you want to break through some of those barriers. Some pesticides have proven to have negative effects on wildlife, for example, frogs. Do you know if any organisms are being impacted by enhanced weathering? Good question. I mean, other than mining, which can have negative consequences for biodiversity as we, produce roads and buildings and infrastructure, those materials come from somewhere. They do come from the rocks. So we have to be cautious with where we're getting those materials. And, the mining industry, I think the people I'm working with are well aware of these challenges and want to become a part of the solution, especially in terms of carbon sequestration. But I'm not sure if the enhanced weathering process could have those kinds of negative effects. I would suggest probably not. We are talking about grinding up rock that has really good potential for creating soils. Volcanic soils are among the most fertile soils in the world. And that's the kind of rock we're using when we're deploying metabasalt and basalt. So I think that in large measure, it's hard to think of what those negative consequences will be, except that we have to be cautious against certain materials that are enriched in heavy metals. So thank you for that question.
So it is 4 o'clock now, and I know you have another meeting coming up soon. So I want to thank you so much for coming in and giving us a very, very interesting talk. It was great to have you.
Well, my pleasure. Thank you, Peter. Well, thank you, everybody. I apologize I couldn't get through all 48 questions here. I did my best, but look, these are incredible challenges. The take-home message here is the 10 by 10 by 2050 challenge. We do have to find ways to get the world to transition to negative carbon emissions. We have to start demonstrating these technologies and approaches today if we want to have a chance of getting to billions of tons by 2030. A lot more work needs to happen. But I believe that the soil can be part of that solution set. It will not save us. We still need to cut emissions, but it can help facilitate opportunities to widespread negative emissions if deployed safely and effectively. So thank you everyone for your time, and have a great rest of your seminar. There's some awesome people coming to speak to you. I'm super excited, and I'll talk to you later.
Great, thank you. Bye-bye.
Bye.